We're going to move on now to our next technical session starting now. We're pretty much on schedule, and this one is going to be presented by Thomas Dumoulin, who I will just allow to start sharing his presentation so that he's able to get started. You may have noticed on the wall behind me, I don't know whether you can see on my webcam, there's a picture of me on a bike. And when in some of my spare time, a bit like Israel, I like going out on my bike. And when I saw that we had a Thomas Dumoulin who was going to come and speak to us today, I didn't realize that we had a specialist cyclist who was also a flight test engineer. But I see from the screen that it's not the same Tom Dumoulin. I don't know whether you often get confused or not, Thomas.
Yeah,
but...
very often. I get it very often, especially in the Netherlands, of course.
For sure.
It's actually a more common name in the south of the Netherlands, where I come from. And the biker is also from the south. So
okay, well there we go. So Thomas, if he's not a cyclist, there's many other things that he does, and I can see here in the notes in front of me that he's filled his time with lots of activities, including flying aeroplanes without engines. Another one of those crazy people who's happy to do that, but also a skydiver. So you don't even need to stay in the aeroplane, Thomas. So I'm
actually
very by that.
Yeah, flying aircraft has been is in the past for me. I only jump out of aircraft nowadays.
Okay, well, I hope it's not because you're scared of the aircraft. As flight testers, we make sure that the airplanes are safe. I hope it's just for the pleasure of flying through the sky afterwards. So, so yes, Thomas works at the NLR in the Department of Flight Testing, and he's going to talk to us today about, let me see the title of the presentation. Oh, it's written on the screen for me. So he and his colleagues have worked on an alternative approach for determining the position error corrections. So with that said, Thomas, I will leave you the floor, and before you start, I would just say thank you to you again. I know we talked about this morning, for getting around the various technical challenges to be with us today, because you're working for the NLR, but you're actually presenting to us today from Germany. So yes. I know that hasn't been easy, so thank you again, and the floor is yours.
Yeah, no worries, thank you. So thanks for the introduction. Yeah, this is the usual slide that we have in the beginning of our presentation at NLR, just for safety purposes. So first, the contents of my presentation. I will start with a short introduction. Then I will move on to explain a little bit about what is the position error correction. Now, I think that's something that most of us know, but just to refresh our memories. Then move on to the current state of the art, what kind of approaches and methodologies are currently used to determine the position error correction. And then I will introduce the novel approach that we developed. Then I will show you some of the results, and I will end, of course, with some conclusions. So first, the introduction. Nowadays, aviation still relies on pressure measurements to define the altitude. Each aircraft measures the static pressure, and with that we define an altitude. But also we know that the airspace is becoming more and more crowded. There are more people who are going to fly, there are more flights, and that means that the accuracy requirements on that pressure altitudes are increasing. And actually, recently they have increased in a certain airspace, which we call the RVSM airspace. Yeah, the requirements become more strict on that measurement. The problem is that the aircraft itself induces an error on your measurements, and that error can be corrected for. So that means that the objective is to determine this error for your aircraft so that you can correct it. And for our research, we decided to use our own research aircraft, which is a Cessna Citation II. So the position error correction. Well, we know that air data is measured on probes always on the aircraft structure or in the vicinity of the aircraft structure. And we also know that at subsonic speeds, the flow field that is created around the aircraft extends in all directions, and actually for a considerable amount. Usually it's about 1 to 2 times the span of the aircraft, so it's a large amount. This airflow, this flow field, changes the static pressure as well around the aircraft. And that means that if you make a measurement in that in that flow field with your aircraft, you make an error, and we call that the position error. because it's sensitive to the position of where you put it. We also know that the flow field is unique for each aircraft and each aircraft configuration, and also the flight condition. If you look in the top right of this slide, you see a side view of an aircraft, typical aircraft, and below that you see the pressure distribution, so the difference between the atmospheric static pressure and the local static pressure, and you see it in the graph that it changes along a line drawn on the side of this aircraft. There are certain points here that are indicated here by 1 to 6, where the error is almost 0 or exactly 0. However, if you change the aircraft configuration or you have a different flight condition, this curve will change. And that means that it is impossible to find a location on the aircraft where the position error is 0 for all flight conditions. And therefore, we must correct this error to make the measurement more accurate, and that's what we call the position error correction. So we decided to have a mathematical formulation for the position error correction in static pressure. And we decided to represent it as a function of the dynamic pressure. So 1/2 times the density times the true airspeed squared. And in front of that, there's of course a pressure coefficient. And we also observed that this pressure coefficient does not remain constant with changing dynamic pressure. So change in altitude, the density changes, or a change in speed also changes this pressure coefficient. And that means that the pressure coefficient must be represented as a separate function as well. And we decided for a polynomial expansion as a function of the inherent flight characteristics. So the example you see here, it's on the Mach number, the angle of attack, the side slip angle, and there's also a Reynolds number term in there. And of course, you can add as much high order terms as you like. The more high order terms there are, the more accurate the polynomial function becomes. But usually a few orders is sufficient for the accuracy that we want. Now the main goal is now to determine these constants in this polynomial, the C0, C1, etc. To determine the function of the pressure PEC. Currently, that is mostly done by means of flight tests. Now, I will show you some currently used methods for flight testing. One of the most popular is the tower flyby. Here, the aircraft flies by a ground station or a tower, and on the ground or on the tower, the static pressure of the atmosphere is measured. As long as there is not much wind, the pressure is very accurate on the ground. The measurement is very accurate on the ground. The aircraft then flies by the tower or by the ground station, and the aircraft itself measures its own static pressure, of course, with the error there. Any small differences in altitude between the tower and the aircraft can be measured and corrected for. So the difference between both measurements then becomes the PEC. Two more very much used methods are the trailing cone and the static bomb. Here you have a measurement device which you extend behind or below the aircraft far enough so that the reference pressure is not influenced anymore by the aircraft. Of course, the advantage for this is that you can reach multiple speeds, but also high altitudes. The disadvantage for this is that you have a large structural modification to the aircraft because you have to mount the system on your aircraft. There are also certain maneuvers that can be flown, like for instance a cloverleaf pattern flight. And of course you can use a pacer aircraft, which of course one of the two aircraft has to be already calibrated or have a calibration device on it. There are of course more methods and more combined methods, but these are just a few that I wanted to present. Then our methodology. It actually consists out of 3 parts. We start with calculations, so computational fluid dynamics. Of course, this is a very cheap method. It's not flight testing, but it's cheap. And we make a priori model with the computational fluid dynamics. So we make the first estimation of the polynomial that I showed earlier. We then use the conventional tower flyby method to validate and tune that model. And we end, and that's actually the novel part of our approach, with extrapolation flights at altitude. And we have two different maneuvers that are complementary to each other. We can do accelerated, decelerated maneuvers, and we can do some steep turns. And I will come back to that later. So first, our instrumentation. We have two locations on the aircraft at which we measure the static pressure. We have the holes on the fuselage that are already there on the Cessna citation. And then we have an additional nose boom that is mounted on the citation with one single orifice also on the nose boom. And of course, on the nose boom, we also measure the angle of attack and the side slip angle with vanes for more accuracy. So the novel methodology first has a priori model that we obtained from the computational fluid dynamics, and we check that against a hard reference using the tower flyby. And if needed, the parameters that we determined with the model will be validated or tuned using that hard reference as a data. But then we only have the data on the ground, and we also want the data in the air at high altitudes. And there we use what we call a delta mode, where we measure everything in delta, so in differences. So we take differences between measurements, and if the static pressure of the atmosphere remains the same during a flight maneuver, then the difference in your measurement becomes the difference in the PEC, in the position error correction. And that way we determine the PEC at altitude. Of course, the main thing for this method that must apply is that the static pressure of the atmosphere remains the same during that maneuver. And I will come back to that later as well. So first, the aircraft has a flight envelope, and like I mentioned previously, we want to cover the envelope. Actually, the lowest solid black line that you see in this Mach number versus angle of attack plot, that's at sea level. So that will be the tower flyby, the hard reference. And then the dashed lines will be the flights at altitude. And the way we move through these lines is by means of an acceleration-deceleration run. So like I mentioned previously, we want the static pressure of the atmosphere to remain the same during one of these maneuvers. So during, for instance, a acceleration-deceleration maneuver. And for that, we use weather models at altitudes. So if you look at this picture, you see a weather model at a certain altitude above the Netherlands at a certain day. And this was quite a convenient day because here the isohypsal lines that you see on this graph are straight and parallel to each other, and that's what we want because we want to fly exactly on these lines. Now, an isohypsal line is a line that looks a bit like an iso bar line, but it's a little bit different because it's also a line of constant altitude. So actually it's a line of constant pressure and constant altitude. And it means if you follow these lines, your static pressure of the atmosphere will remain the same. So prior to the flight, we look at the weather predictions, and with that, we decide where and when we are going to do these maneuvers. So moving on to some of the results. We started with the computational fluid dynamics. We made a very high detailed 3D scan of the front part of the aircraft, where the accuracy is most required. And of course, we measured for CFD calculations. And then you get the nice colorful pictures. This is just one side view of the nose of the aircraft. What you can see here is you see the location in front of the aircraft in the blue, where the static pressure measurement on the boom is mounted. And of course, on the aircraft itself, you see in the orange-yellow part, the measurement orifice of the fuselage. And the thing that we observed first is of course that in front of the aircraft we have a higher pressure, and on the fuselage of the aircraft we have suction, so a lower pressure. So the magnitude of the PEC is actually of opposite sign compared to the two sources. So after CFD, we did the ground station flybys. The ground station consists of a GPS system. So we measured the GPS location of the ground station and also on the aircraft. We use the GPS to correct for the altitude difference between our ground station and the aircraft as it flies by. And on the ground in the car here, we use a digital air data computer similar to the ones that are on board. And in the lower picture, you see that we have a meteorological tower on which we put measurement devices. So we measure the temperature and humidity on 2 different levels, so that we can predict how the atmosphere is during the flybys and correct even the altitude differences better. So the tower flybys were conducted, it was 2 years ago on Eelde Airport in the north of the Netherlands. We had very good weather, as you can see from the images. It was in the evening, so it's very good weather for tower flybys. We did 2 separate flights. One was at lower mast than the other one, and that was basically to decouple the correlation between the Mach number and angle of attack. Yeah, some results of the ground station flyby. You see a graph here of the PEC that we got from the flybys versus the Mach number. If you red dots, those are the ones that are from the boom. So you see a positive number of the PEC, and the blue dots are the one from the fuselage, and those are negative, so of opposite sign. But also, if you look at the cyan dots close to the fuselage line, those are actually the a priori model, the CFD predicted PEC on the fuselage. And you observe a large difference here. So tuning or the PEC formula was required against this hard reference. And then, of course, we moved on to the extrapolation flights. This is just one of the flights that we did. This particular flight went to 3 flight levels: flight level 120, 200, and 300. And at each flight level, we did our maneuvers. And these maneuvers, we started first with a steady run. So just flying parallel to these isoheaps and at a constant speed, constant altitude. And with that, we scan the atmosphere. So we check the atmosphere if it really stays constant, like the weather models predicted. Then we turn around and we use the same track to do an acceleration deceleration run. Again, we turn around in the opposite direction. Again, we do another acceleration deceleration run for redundancy. And then again, we turn around and use the same track for another steady control run to also observe the changes in the atmosphere over time. So looking at some of the graphs that we got from one of these acceleration deceleration run, and you see here, if you look at the Mach number graph, you see an acceleration and deceleration. And then next to the Mach number graph on the left side, there's a GPS altitude. So we also observed that the GPS altitude does not remain constant during these acceleration deceleration runs. And that's mainly because our autopilot is not capable during an acceleration or deceleration to really keep that GPS altitude exactly the same. So there's a slight variance, but of course not a problem because we measure GPS very accurately, so we can correct for it. Another graph that is interesting to look at is the pressure match on the left side. The red line there is the raw pressure difference from the boom mounted hull. And once that is corrected for the PEC, it matches the pressure that the GPS altitude would indicate. So the conclusions. We determined the PEC of the citation within an accuracy of 35 pascals in the entire flight envelope with 3 sigma. So yeah, that's not only at high altitude, but also on the ground. The achieved accuracy was actually validated twice in 2 years ago by means of tower flybys here at Manchin Airport. We also observed that the influence of the atmospheric conditions was more than expected, and we saw that especially in our scans of the atmosphere. The weather prediction models are, of course, models. They are very coarse. They have a grid of 2 by 2 kilometers. And we observed that there are slight differences between the models, what's predicted, and what's really happening in the atmosphere. And of course, yeah, turbulence influence your the accuracy of your measurement as well. So we need to stay away from the jet stream, especially the boundary of the jet stream. And also what we observe is that CFD gives a very precise result, but not accurate enough to allow no flight testing at all. So that's positive news for us flight test engineers, because we are not yet out of a job. Are there any questions?
Oof, phew! I was worried that I was about to have to resign.
Yeah.
So, Thomas, thank you for your presentation. I have to say, it never ceases to amaze me. I think I've been going to Society of Flight Test Engineers symposiums for over 10 years now, and I don't think I've ever been to a single one where there hasn't been at least one presentation or discussion about the subject of position error corrections or anemometric calibration. And it's such a fundamental part of our flight testing activity of the vehicles we fly on, and yet we see that there are still new things to learn and new ideas coming along all the time. So that's really good to see. Some questions have been coming in on the chat from Lisandre, who asked us yesterday. Actually, some of the answers are already there, but perhaps you could expand a little bit. Her first question was talking about the accuracy of the weather models, and you're right, you did touch on it on your your conclusion side. You mentioned the coarseness of the grid, which obviously is one of the parameters. But I'm also interested in, even if you had a particularly fine grid, how could you be confident about those predictions, and is the error on those predictions bigger than the PEC that you're trying to measure?
No, the error is actually smaller than what we're trying to measure, but still significantly large. The problem is that these models are usually measured by means of weather balloons, and of course a weather balloon is a single point that moves at a trajectory to the air with the wind. There's no steerability, and I think that really defines the inaccuracy of the models. And of course they also use computational fluid dynamics for the predictions, and as computers increase their capabilities, these models will become more accurate in the future. That's what I think, but right now it's still not that accurate enough.
And you've never considered doing, I don't know, local sampling or your own sampling in the area? You prefer to use, I guess it's a very expensive exercise to do that.
Yeah, actually it's just very expensive, and that's what we actually do with the steady run at the beginning of our, so before we do an acceleration deceleration, we do the scan to check what the atmosphere actually is compared to the models.
Okay. A question also came in from Sean DeSalvo, who asks why you take a humidity measurement on the ground. I guess there's potentially two aspects to that. Why do you take a humidity measurement? And secondly, why on the ground?
Well, humidity influences your air density. The thing we get taught in school is always we use numbers for dry air. In real life, it's never dry, especially not in the Netherlands. It's very, very moisture.
I didn't want to say anything.
Actually, on that evening, it was very nice weather, but still, it was very cold in the evening, and I measured almost 100% humidity at the end of the evening. So it's very humid, and that influences your density a little bit. And the density used, of course, for the correction of air pressure between the height of the aircraft and the ground station.
Okay, thank you. And we had some questions now coming in from India. So you can see you've got a worldwide audience. Kalyan is asking that you mentioned an expression for the CP as a function of several parameters. He thinks it's on slide 3, so I don't know whether you can throw that up for us.
Yeah, I go back.
And he had a question as to which was the last term. What was the definition of it? Let's have a look when we come back to slide 3.
Slide 3. Yeah, this one. You mean the HOT?
HOT, yes.
HOT, yeah, it's high order terms. It's an abbreviation for high order terms, yeah. So, like I said, you can add as much terms as higher order. So to the 3rd power, to the 4th power, or you go to infinity if you like. If you increase the order, you get more accuracy, but usually a few orders that we see already here is sufficient for the accuracy that we want.
Okay, so it's a generic grouping term. Okay,
Yeah.
I think that answers Kalyan's question. We also had a question from Senthil, also in India. He's interested about the FTI which you were using on board the aeroplane. I don't know if you can say a few words about what you've got on board your citation.
Yeah, actually, I think I have a slide for that. No, I don't have it. But yeah, we have, of course, GPS on board, and we correct that after in post-processing, so that we have a very accurate GPS measurement, because we need to provide the altitude as well. And in the back of the aircraft, we have the IRS, Inertial Reference System, which we use to determine the angles of the aircraft. And then also in the back of the aircraft, we have 2 digital air data computers. One of them is connected to the fuselage, and one of them is connected to the air data boom. And then again, that's what I did show. We have an air data boom in front of the aircraft, for which we measure the angle of attack, angle of side slip, and also an additional static pressure.
Okay, thank you for that description. I seem to remember in a previous conference we might have had a paper about the instrumentation on your aircraft, because I know it's used for many different projects. So I guess you're always reusing the same instrumentation rather than starting from zero each time.
Yeah, exactly.
Another question which has come in from Jeremy. I don't know, Jeremy, where you are, but welcome to our session this afternoon. And he's got another question about the weather models, and he wonders whether you use them as an input for your method, or are they simply used to identify a suitable test zone?
The second one, just for the test zone. We don't use them as an input. It's also not necessary. You just want to know at what location and what time, what altitude, and what heading we should fly. And what is also possible is that if you look at these lines of, if I can go to the slides of the isohypsen. If you look at these lines at altitude, the isohypsen, usually the wind direction moves parallel to these lines. So what we also did is looked at our flight management system to see what the wind direction is, and provide some last corrections on the heading to really have the heading of the isohypse.
Okay, perfect. It sounds like you're taking data from every possible source to try and fine tune the results. So.
Exactly. Yeah.
And still on the subject of weather, Kartik, who's also in India, he wonders if any temperature inversions have an impact on your method. How do you have to deal with those?
That's a good question. I haven't looked into that yet. I think we didn't encounter that at this moment.
You mean it's always cold in the Netherlands? It never does it any other way,
cold,
right?
Yeah, and especially at altitude, of course. Yeah. But like I said, we also measure temperature on the ground for the flybys, and we have a very accurate total air temperature probe on the aircraft. So we also measure temperature. Okay.
And Paul is just commenting that you have a good relationship with, it's KNMI, but I guess that's the Met Institute in the Netherlands. Is that right?
Yeah, that's something that we still have to do. We have to contact them to see if we can help each other. They can provide maybe more accurate weather predictions, and we can help validate their models.
Yes, I was involved in another conference not so long ago where people were exploring the idea that you could actually feed weather models with data from flying aircraft. The so-called aircraft as a weather sensor model. And yes, I'm sure that all of these organizations would be delighted if they got that feedback. Obviously, there's a lot of technical challenges associated with measuring that data and getting it to the right institutions, but it's certainly something which I think has a future. So.
Yeah, as long as you have the PEC of each aircraft very accurately, you can measure very accurately.
Exactly. But hopefully, if the aircraft has been certified, it should be good. So.
Yeah, exactly. Well, that's something that we observed with our citation. It's of course certified for RVSM, but we can see in the digital air data computer 1, so the computer that's on board, there's a correction there already. Cessna citation, Cessna predicted, but it's much worse than our calibration. It's of course enough for RVSM, but we are more precise.
Okay, That's an interesting feedback.
Yeah.
Okay, well, we're at the end of our time slot, and in fact, there are no more questions anyway. So, Thomas, thank you very much for taking time out of what I know is a busy schedule for you at the moment and for sharing that presentation with us. You can see from the number of questions that even if it's an old subject, it's still one which is very passionately discussed and debated. So I'm sure we'll carry on talking about it in the future.
Yeah, thank you very much.